Okay, so yesterday we had talked about calculating our omega. We ended with the revolutions per minute, although that was a little hurried. But it ends up being 280 revolutions per minute. You could use dimensional analysis to convert from your radians per second. And let's kind of go over how to do that, right? Okay, so I'm going to use the 29 radians per second. And we're going to revolutions per minute, right? I know. I already addressed that. So how many radians would go on the bottom here? 2 pi, okay? So we want 2 pi radians, and you need to put that in parentheses, okay? If you don't put that in parentheses and you just type in 2 pi in the denominator, your calculator is going to divide by 2, and then it's going to divide again by pi. You want it to divide by the quantity 2 pi, okay? And so then on top, that's going to equal 1 revolution, okay? Now we need to convert the time, all right? How many seconds do we have here on the bottom? What number goes in front of seconds? 1, right? Okay. Now, where does the other seconds have to be to cancel out? On the top, okay? How many seconds? Because we're trying to get to minutes here. 60, all right? So 60 seconds equals? All right, fantastic. So now we can go through and cancel out our units. So radians cancel radians, and we're left with revolutions on top. Seconds cancel seconds. You're left with minutes on bottom. So that would give us the unit revolutions per minute. So type in your calculators, please, and let's just confirm that it's 280. Remember, you need to use the actual pi button on your calculator. Don't type in 3.14159. Okay, so what do we end up with then when we have 2 sig figs like we're supposed to? Very good, just like we got. What's up?
Can you use the original 3.5 revolution? That's what I did.
Yeah, you could do that. Okay, cool. All right, so here it just is telling you what I told you a second ago, that you need to put your 2 pi in parentheses. Now let's move on to acceleration, okay? So it says, what is the equation for acceleration? So I'm looking for the equation for average linear acceleration from way back in the day, all right? What was the equation for the average acceleration? I'll give you a hint. It's divided.
Delta V over delta T.
Fantastic. Okay, delta V over delta T. All right. Now we want to come up with the counterpart for angular. All right. So the symbol for angular average acceleration is alpha, lowercase alpha. I call it fishy thing. Okay. Yeah, that's why I call it fishy thing. So, but that's lowercase alpha. All right. I don't remember, honestly. Okay, so now I need to do the counterpart for velocity, right? So we have linear velocity over in this linear system. What did we say the angular velocity symbol was from yesterday? Omega. It's not a W. It's an overcurved W. What? Okay. All right. So we're going to say, but what about omega? Like delta omega. Very good. Okay. So it's going to be delta omega. Yeah, it looks like a butt. All right. You can call it the booty. Adam's like, I will not participate in such nonsense. Okay. Okay, so now we have the average angular acceleration. Okay. All right. Questions about that? Yes, no? Okay. Okay, so here's a question. A figure skater begins spinning counterclockwise at an angular speed of 4.0 pi radians per second during a 3.0 second interval. She slowly pulls her arms inward and finally spins at 8.0 pi radians per second. What is her average angular acceleration during this time interval? Okay, so you've seen figure skaters or ice skaters or whatever do that before, right? Yeah, they start doing a spin and their arms are out, and then they pull their arms in and they start going much faster, right? You maybe have done something like this where you've been sitting in a roller chair, like a spinny chair, and you spin yourself around and you put your legs out and the chair slows down, and then you pull your legs back in and the chair speeds up. Have y'all ever done that before? Yeah? Okay. That's angular momentum is what you're seeing there, okay? We would talk about that in AP Physics. Angular momentum is not going to be part of this course, all right? But that's why you speed up or slow down is because of angular momentum. Question. Oh, yes, good question. So on this previous page here, the equation for average angular acceleration is a boxed equation. So I will give that to you on any quiz or test. And we also need to look at the units for that, okay? So let's come up with our units real quick. All right, so what's the unit for angular velocity? Radians per second. That one was the standard one, right? Okay, and then what's the unit for time? Second. So this is going to be radians per second per second. So what do you think we could call that? Radians per second squared. Very good. Okay, so the units for angular acceleration are going to be radians per second squared. That's going to be standard. Okay, all right. Okay, so now it says here that she starts out at 4.0 pi radians per second, and then she ends up spinning at 8.0 pi radians per second. So we can definitely see that her angular velocity increased over this time interval, right? Okay, and it's asking you for the average angular acceleration. So what equation do you think you're going to use? The one we just got. Very good. So we're going to say alpha is equal to, and it's delta omega, right? What's delta mean? Change in. So what is that?
The
Final minus the initial, okay? So we're going to write that down. We're going to say delta omega over delta t, which is going to be equal to the final omega minus the initial omega over delta t. So, we're going to say 8 pi radians minus 4 pi radians over, okay, now this bottom one, I already gave you the time interval, okay? I gave you the change in time, 3 seconds, okay? So that's what we're going to put on the bottom then, 3 seconds. All right, so go type that in your calculator, and let's come up with an answer. All right, who's got it? Brady?
You want the whole number or just the sig thing?
The whole number, please.
Okay, 4.188790205. Radians per second squared.
Very good. Okay, now we want the sig fig answer. So how many sig figs should we have? 2. Very good. All right, Mark, so what's the answer? All right, very good. Radians per second squared. Okay. Nice. Does that make sense to everybody? Is that super easy or what? Sure. Slide back up to the problem? Okay. All right. Okay, so once upon a time, when we were talking about linear motion, we had some UAM equations, right? Okay, uniformly accelerated motion equations, and now we're going to have U fishy M equations, okay, or U alpha M equations, and those are going to be your kinematic equations for the angular system or the rotational system. Graham? Yes, they are.
So both of them will be given first?
No, these you have to know. Okay, your linear ones you still have to know all of those. However, I'm going to give you the angular ones, and of course, I hope that you can see. So long as you know that theta, which is angular displacement, corresponds to delta x, which is linear displacement, then you've got that one. You could go backwards. Yeah, you could go backwards and get your linear equations if you ever needed them. All right, but I will provide to you, because I'm nice, the UAM equations. But I will never give you these. Okay, but you should be able to come up with those. All right, Adam. I would if I were you. Yeah. Okay. So, Garrett.
Is that a little F? Can you like zoom in on that?
Yes, I can zoom in on that. Okay, let's see here. Yeah, it is. All right, so it's omega final minus omega initial divided by 2 times t. Okay? All right, so you need to write those down, okay? These are your U alpha M equations. How many angular kinematic variables do you see? Oh, dear God. You're hurting my feelings. 5, thank you. All right. How many angular kinematic equations do you see? If you know any 3 angular kinematic variables, then you can solve for the other 2. And very good. Be left with 1 happy physics student.
Is that A for the fishy thing?
It is the fishy thing, yes.
That does not look like a fishy.
It is. That's fishy thing. That's fishy thing. That's fishy thing. Guys, you're in rotational. All of this is rotational, so you need to be using rotational variables, okay? Let's list those rotational variables so that I know that you know them, okay? So you're going to have theta, that's your angular displacement. You're going to have omega final, so that's your angular velocity final. You're going to have omega initial, that's your angular velocity initial. You're going to have alpha, that's your angular acceleration. And you're going to have time, that's your time. No, it is not. Mm-hmm. It's just weird. Okay. Like Graham said, these are boxed, so I will give this to you on any quiz or test. Some key important things about these equations: you must use radians when you're plugging into these equations. You cannot use degrees, you cannot use revolutions. You have to be in radians. So if I give you your theta in degrees or revolutions, you need to convert it, okay? Alpha, it must equal a number, all right? Alpha cannot be changing in any of the problems that I give you in order for you to use these, because this is uniformly angularly accelerated motion. If the angular acceleration is not uniform, in other words, it's not constant, you cannot use these equations, all right? So in your problems, if it shows alpha is changing, don't try and use this. It's not going to work, okay? Only when alpha equals a number and stays that number can you use these equations, all right? Questions? Then it's uniform. Just like in linear kinematics. No, alpha is fishy thing. Omega is the booty. I would say, a wheel is spinning at, 4.6 radians per second squared and accelerates to, 6.9 radians per second squared. What's blah, blah, blah. Something like that. All right. So here's a practice question. Why does that say care? Oh, I really hate that. That's supposed to say car. All right. There you go. A remote control car's wheel accelerates at 22.4 radians per second squared. The wheel begins with an angular speed of 10.8 radians per second. What is the wheel's angular speed after exactly 3 full turns? Okay? So what are we asking here? What do we want to know?
The velocity final.
Yeah, the angular velocity final, right? So let's kind of list stuff that we know and that we want to know like we used to, okay? So we want to know what the angular velocity final is, all right? Somebody raise your hand and tell me something we know. All right, somebody other than Shabam, he just said the first one. Graham. What do we call a fishy thing? Okay. All right, perfect. Somebody else? Sean? All right, omega initial is equal to 10.8 radians per second. What is omega? What is that? Angular velocity, very good. What else do I know? I know one more thing. Adam? No, I don't know that. Garrett? It's just, yeah. It tells you that it's after exactly 3 full turns. So that is the entire change. Three what? Revolutions. Very good. Yeah. Okay. Now remember, like we said, you can't use anything but radians when you're plugging in for theta. So instead of 3 revolutions, we need to say that 1 revolution equals how many radians? 2 pi radians. Okay. So that's going to give us 6 pi radians as our delta theta. Okay. All right, so now we need to find an equation that has only those 4 variables in it and nothing else, okay? It's going to have omega final, omega initial, alpha, and delta theta. Okay. All right, so we're going to use the squared one, okay? Okay, so we can say omega final squared equals omega initial squared plus 2 alpha times delta theta. You got that memorized already? I hope so. Nice. Because you know how we had a quiz over them when they were in linear form? Not your memory quiz. I might make you take a memorizing quiz.
You said you're going to give them some.
Oh. Okay, so do I want to solve for omega final squared? No. So what should I do? And what happens when I add a square root into something?
Plus or minus.
Very good. Okay, so I'd like you to go ahead and start plugging your values in. Don't forget to square your initial angular velocity. All right, who's got it? Josh. Just the answer, please.
30
All right, 30 radians per second. Raise your hand if you agree with that value.
I do.
Very good. Oh, of course you do. Okay, now the plus or minus deal. That indicates clockwise or counterclockwise. That's the direction, okay? You know, like in linear, we could be left or right, up, down, back, forth. In rotational, you're going to be clockwise or counterclockwise, okay? And that has to do with the unit circle, all right? the unit circle starts out at 0, then it goes 90, then it goes 180, then it goes 270, right? So if you work your way counterclockwise around the unit circle, you are increasing the value from 0 to 90 to 180. So that is going to be positive. Counterclockwise is positive. Clockwise is negative, okay? So in this case, did they tell us which way that car or the wheel was spinning? No, they didn't. So we can't decide here. We're only going to be able to give the magnitude this time. So we know that it's going to be an angular velocity of 30 radians per second, but we don't know if it's going to be clockwise or counterclockwise, okay? Clockwise is going to be positive. That would be a positive value.
Wait, I thought you just said
I mean, excuse me, I'm sorry. Counterclockwise is going to be a positive value. And clockwise would be a negative value. Depends on which direction the car is. Right? What if he's in reverse? Okay. All right. Cool. Maybe. What now? Yeah, we don't know if it's positive or negative. We're just giving the magnitude right now. Okay, so this right now, that's magnitude only. Okay, so our little circle activity out there just showed us that as the radius increased, what else increased? The tangential velocity increased, and something else did too. Arc length. Very good. Okay, so we're going to say then our formula is r times theta for arc length. Okay, and since theta is a constant, we can get rid of it when we're doing proportion statements. Okay, that means that arc length is proportional to the radius. That little symbol there, the fishy symbol, unfortunately, it also means proportional to. Okay, so arc length is proportional to radius. That means if the radius increases, then the arc length must increase. Okay. Now we have two formulas that we're going to look at. Only one of them is boxed. Okay. This one right here is going to be your boxed formula for tangential velocity. Tangential velocity will be equal to the radius times the angular velocity omega. That's the one I'm going to give to you. All right. So if we were to look at the proportion statements there, tangential velocity equals r times omega. All right, so the larger the radius, the larger the tangential velocity. As we looked, or as I asked you questions a little bit ago, remember omega was equal to delta theta over delta t, right? And we said that every single person in that line traveled through exactly the same omega, and they traveled through exactly the same t. Does that make sense? Okay, it took them the same amount of time, and they traveled through the same angular displacement. So this is constant. We can get rid of it when we're looking at proportions. And we can say then that the tangential velocity is going to be proportional to the radius. So if the radius increases, then the tangential velocity must also increase. Garrett? Yeah, it's a bad T.
Wait, so is that equation dt equals r times t? No,
R times omega. Okay. Yeah. Are you like up here?
The one that you bought.
Yeah, that's VT, tangential velocity, equals R times omega. Yeah, we will. Now, what now? This alpha down here stands for proportional. I don't think I've ever seen that. This doesn't mean you can't. Proportional. Yeah, you could do something like that. Yeah. All right. Now, the boxed equation up there, that's the only one that I'm going to give you. This other one that I'm about to talk about down here, if you wanted to use that one, you need to either be able to come up with it on your own or have it memorized. Okay. Garrett, you had a question? I'm going to get there in just a minute. Okay. Um, for example, like when a rocket, when we want to send a rocket to space, the Earth is a sphere, all right? That means it's going through a circular orbit. If anything is going to shoot off of Earth, it has to overcome gravity to do that, which means it has to move at a certain tangential velocity. We should be able to calculate what speed does a rocket have to reach in order for it to break out of Earth's gravitational pull and make it into space. What movie?
There was a movie where they had to use the moon.
The Martian. Gravity.
It was like
Interstellar.
Apollo something.
Apollo 13.
Yeah, that one.
Yeah.
And then it like there was a picture just like that in the movie. I'm not even kidding.
Awesome. Okay. Now let's look and see how do we come up with this second equation down here. Tangential velocity is also equal to arc length times time. Okay. Well, first off, if we say that, do what? Divided by my bad. Divided by time. Okay. If we know that tangential velocity is equal to the radius times omega, and we know that omega is equal to delta theta over delta time, and we know that the arc length is equal to radius times theta, what do you think we can do here? What substitutions do you think we can make to try and come up with that new equation down there? How did I get that? Where did that come from? What now?
W. Plug that.
W.
Omega.
Omega. Okay. So what about omega? What do you want to do there?
You change it into the delta theta over.
Cool. So if I say omega equals delta theta over delta time, okay?
And then r over 1.
Yeah. Why don't I could take this stuff right here, and I could solve for theta, right? So I could say that theta must be equal to S over R. Does that make sense to everybody so far? Okay. So then that means that omega would be equal to S over R over delta T over 1. Right? So I have that complex fraction. How do we undo complex fractions? Very good. So I could say 1 over delta T and 1 over delta T. That goes away. So that means omega is equal to S over RT, right? Okay, now we want to get some tangential velocity business in there, okay? If tangential velocity is equal to R times omega, and this stuff right here is omega, can I plug that in there? Okay, so let's do that then. So we're going to say, bless you, tangential velocity is equal to R times arc length over R times delta T. What do you see? Yeah, I can cancel my R's out, which means that my tangential velocity then is also equal to arc length over time. Everybody good with that? Okay, so you can either go through those algebraic manipulations and come up with this equation on your own, should you ever need to use it, or you memorize it, okay? Because the only one I'm going to give you is the one up above, R times omega. Okay? Questions? Okay, now let's see if we can come up with units for tangential velocity, all right? So let's do this two different ways. Let's see, tangential velocity was also equal to R times omega, right? Okay, so units. What is the unit for arc length? For arc length? Meters, okay? So we would get meters divided by, what's the unit for time? Okay, so according to the tangential velocity formula that uses arc length over time, you get meters per second. Let's do it for this next one here. What's the unit for radius? Meters times. Now, what's the unit for omega? Radians per second. Okay, radians per second. Now, We said tangential velocity was a linear velocity, right? Look at the units here. They don't match so far. What, Graham? Radians have no place in the linear system. They are a unitless number, right? So as soon as you switch over from a rotational or an angular system to a linear system, radians go away. So what unit do you come up with? Meters per second, all right? And that makes sense for a linear velocity, meters per second. That's what we've been used to all along, right? Okay, so meters per second is the unit for our tangential velocity. Why did I put this half arrow over the top? Yeah, that it's a vector, okay? So you got to have magnitude and direction. Everybody with me on that? Okay, now let's look at this picture up here that Garrett drew our attention to. Okay, notice that these are all velocity vectors that are tangent to the circle. Who can tell me what tangent means? Adam? Very good. It only touches the circle at one point, okay? So each of those is tangent, all right? Now, let's see here. We can answer another question. I'm going to take my stopper on a string here, and I'm going to spin it around in the air in just a second. And right when the stopper gets to this position right here, I'm going to let go of it, okay? Will the stopper move in direction A, direction B, direction C, direction D, okay? I want y'all to think about that for just a second, and then raise your hand when you think you've got it. What's up? I'm going to hold the stopper horizontally and spin it like this, okay? And then I'm going to wait until my stopper gets right here, and then I'm going to let go, okay? And I want you to see which path will my stopper move in, okay? Which path will the stopper take?
So once it's like right here, you're gonna stop. Where's it gonna go?
Which way? I'm just going to let go. A, B, C, or D. Which way is the stopper going to go? I have hit a student in the head once by this, okay? All right, so raise your hand if you vote that it is A. Okay. All right.
It's not gonna curve as much. It's gonna be like kind of a.
Raise your hand if you say it's going to be B. Raise your hand if you say C. Raise your hand if you say D. Okay. All right. Let's see if we're right. Okay. It's C because it's tangent to the circle. Okay. Yeah, it's tangent. Okay. As soon as I let go over there on the side. Okay. And I'm not doing a very good job of releasing right when I'm supposed to. 1, 2, 3. There we go. Okay. All right. So did you see it go? It went straight back from where it was supposed to. Okay. Yeah. As soon as I let go, that stopper was right at this position, and that's when the string broke and it moves off in a straight path. I don't know which way you're saying, Adam. I'm set it. No, then I would wait till the stopper is back here. If I wanted to travel that way, I would let go of the string when the stopper was at this location.
There's a straight line going like this.
Yeah. Okay. So let's see. If I want the stopper to go that way, where should I let go of the string? Where should the stopper be? Should it be here? Should it be here? Okay. So if I let go of the string when the stopper is here, then it should shoot that way, and then maybe it'll hit Josh. All right. Let's see. Okay. All right. Okay. Perhaps. He was all about calculating that tangential velocity. Oh, almost got Jen. All right.
I was ready though. Can I spin it?
So close. Okay. Eventually, y'all will have your own stoppers on a string. Okay. Okay. All right. Cool. So that's tangential velocity. Let's do a problem. When you swing a golf club, you happen to swing with a constant angular velocity of 45 radians per second. You are told by your golf partner, who happens to be a physics teacher, the faster the golf club's head hits the ball, the further the ball will travel because of a greater change in momentum. One golf club in your bag has a length of 0.93 meters, and another golf club has a length of 1.09 meters. Which club should you pick? And you're trying to make the golf ball go further away, right? Okay. So, I have some people raising their hands right now, but I bet you don't have any math to back up your answer, right?
I don't have it already done, but I know what I would do.
All right, Adam. Very good. We're going to have a greater tangential velocity if we use that longer club. Tell me why, Adam.
Because it has to go greater distance. Oh, no.
So close. You're so close. Siobhan?
Tangential velocity is proportional to the radius.
Very good. Okay. The club is going to represent the radius, right? So where I'm holding the club, that's the axis of rotation, and I'm swinging that club through this circular arc here. So the club length represents the radius. If I have a longer radius, then my tangential velocity goes up. Let's go ahead and math this real quick. So we're going to say the tangential velocity of club 1 is going to be equal to the radius of club 1 times the angular velocity of club 1, right? And we were told that we're going to swing it with that constant angular velocity of 45 radians per second. So that's going to be 0.93 meters times 45 radians per second. Y'all type that in. And the second one is going to be the tangential velocity of club 2 is equal to the radius of club 2 times omega. So some of you do club 1, some of you do club 2 so that we can get the answers. Yes, please. So what's club 1's tangential velocity going to be? Well, actually, we just have to choose a club. So like that's the answer is just losing. Not within, no, not even if it was within 1 sig fig, no. So, all right, good try there, Graham. All right, so what do we get for tangential velocity of club 1? Siobhan? Yes, please.
42 meters per second.
There you go, 42 meters per second, okay? Who's got the tangential velocity of club 2, please? Josh?
49.
Okay, so which club should I pick? Club 2. Very good. All right. So now let's see. If there is a, listen to me, if there is a tangential velocity, there must also be a tangential acceleration, okay? Because we know that the formula for acceleration is velocity divided by time, right? So if there's a tangential velocity, then couldn't I do tangential velocity divided by time? What do you think that is? Not tangential. Tangential acceleration. Very good, okay? So we're going to have this new boxed equation here. Tangential acceleration is equal to the radius times alpha. Just like the tangential velocity was the radius times omega. It's their counterparts, okay?
I'm going to get alpha and omega.
Again, you must use radians. If you're plugging in there for alpha, you need to use radians. Just like on the previous formula for tangential velocity, r times omega, you've got to plug in radians when you're plugging in omega, okay? So let's see if we can come up with the units just based off of that formula, all right? It's radius times alpha. What's the units for radius? Meters, okay? What's the units for alpha? Radians per second squared, okay? tell me something. What should I do here? Why? Very good. We're in a linear system. Tangential means you're moving in a straight line. This is a linear acceleration. Radians have no place in a linear system. That means that our units then are going to be meters per second squared, just like always.
I have a question.
Yes.
So that stopper when you're swinging it,
Uh-huh.
you let go.
Uh-huh.
Was there like a negative acceleration because it slows down?
I think it came to a stop because it was running out of energy. It was running out of, yeah, it hit something else. There was an opposite force that acted on it. There was technically, yes, in real life, there's air resistance, which means, yeah, the stopper has a negative acceleration. But in this class, what do we say about air resistance? It doesn't exist, right? We're in the vacuum that you can breathe in, okay? All right. Yes, sir. That actually depends on a lot of factors. It depends on your temperature. It depends on how far above or below sea level you are. All kinds of stuff. So the density of air. Okay, good question, though, Adam. All right, now let's talk about centripetal acceleration. Okay, so that means, listen, guys, we've just stumbled upon something pretty cool. An object going through circular motion, okay, has 3 different kinds of acceleration. It's got angular acceleration, it's got tangential acceleration, and now I'm about to tell you about centripetal acceleration. Okay? Yeah, we're gonna have so much fun.
Oh, you're doing a speech.
Okay.
You have 3 points and you gotta expand them. You gotta end with the conclusion.
All right. Thank you. So, centripetal acceleration. The word centripetal means center seeking. Okay. So, anytime you see centripetal, that means center seeking. Centripetal acceleration is always inward, okay? And that's because it's going towards the center of a circle, all right? So if I have my stopper on a string here, okay, I'm going to have a tangential acceleration that moves off in a straight line this way, okay? I'm going to have a centripetal acceleration that moves in a line this way towards the center of the circle, and I would have an angular acceleration, alpha, that's following the path of the curve there. Okay? The centripetal acceleration is what causes circular motion to occur. Okay, it is because of that centripetal acceleration that an object goes through a circular path in the first place. And then we have some equations. Okay, this one's a boxed equation for you. Centripetal acceleration is equal to the tangential velocity squared over the radius. It is also equal to the radius times omega squared. Now, we can look at how do we come up with that, okay? If we take the first formula here, centripetal acceleration equals tangential velocity over the radius, and we take the formula for tangential velocity, radius times omega, and we can plug that stuff in here, right? So that's going to be radius times omega, and then we square that quantity. So that gets us radius squared times omega squared, and then one of these radii can cancel one of those, and that gives us radius times omega squared. So that's a second formula for us to use, okay? You have 2 of those at your disposal, and based off of what information you're given in a problem, you can choose which one's going to be most useful. Centripetal acceleration is also a linear acceleration. As you can see in our picture over here, it's a straight line, okay? It's moving in a straight line towards the center of the circle. Since it's a linear acceleration, the units are going to be the units for linear acceleration, meters per second squared. Everybody cool with all of that stuff? All right. Super cool.
It's so cool.
Okay, good?
Wait, I have a question.
Yes.
Is there centripetal velocity?
No. There's not centripetal velocity, but there is centripetal something else. Very good. Okay. Since there is an acceleration, we know that there must be a force, right? Okay. Force equals what? Mass times acceleration. Okay.
Like when you like take a water bottle, I roll the spin around and then do this, all the water still stays in there.
Yep. We're going to talk about why.